So let's solve a problem involving uniform circular motion. So this problem states that a large cylindrical spacecraft is being designed with artificial gravity for long distance flight. The engineers want to simulate the acceleration of gravity on Earth. What speed must the spacecraft rotate if the radius is 200 meters? So the idea here is that you would have some person standing on the inside of a cylinder like this, and we're looking down the length of the cylinder. If you were to want to look at the side, it would be just like this. And the cylinder would be rotating about some axis that goes through it, and the rotation would be like this. So because this circle is rotating, well, you're going to have uniform circular motion. So this point where the person's standing is going to be moving. And we learned that if you have uniform circular motion, you're going to have some acceleration that's pointing inwards towards the center of the circle, which we called centripetal acceleration. And it would be pointing inwards at every point around the circle. So the basic idea here is that you have some acceleration that's pointing inward, and it's going to work very similar to how gravity works on Earth. So on Earth, we're standing on the top of a sphere, and we know that gravity is pulling us downwards towards Earth, towards the center of the Earth. That is the direction that we need gravity to pull us. That's going to keep us down here on Earth. If gravity wasn't pulling downwards, we would float off into space in that direction. Well, now we need something that's pulling us inward on the circle, but that's also causing us to turn. So what I mean by that is what your body wants to do at this point, if there were no shell that was keeping you here moving along this circle, then if the shell disappeared and you were moving with this velocity, you would just go off in this straight line. So the shell is making your body turn, and that acceleration that you're feeling towards the center of this circle can be the same as the acceleration that you feel that's pulling you down towards Earth. So that's the general idea here. Your body, if the shell was not here, if this cylindrical shell immediately disappeared while you had this velocity, you would want to go off in this straight line, in this direction. So that's how you could simulate gravity on a spaceship. So what we're wanting to find, basically, we want to simulate the acceleration of gravity on Earth. So we want AC to be equal to G. That's the general idea here. We want the acceleration, the centripetal acceleration, to feel the same as the acceleration that you feel due to gravity. So we learned that the formula for centripetal acceleration is AC equals the velocity squared over the radius. And we figured this out in a previous video where we derived this equation using similar triangles. So we now just have to rearrange this equation for the quantity that we're looking to find. So we're looking to find the speed that the spacecraft needs to rotate. And remember also from the previous video that there's no vector hat notation here. This AC formula can't tell you the direction of the acceleration because it's constantly changing, but at any single point, the acceleration is pointing inwards to the center of this circle. Just like with gravity, points towards the center of the Earth. And we can also label this little distance here, so this distance here from the center to the edge of the circle is a radius of 200 meters. So that's useful information that we'll need. So if we're solving for velocity, then I'm going to first rearrange this equation for velocity. So I'm going to multiply both sides of this equation by r, and we have AC times r is equal to v squared. And now we just take the square root of both sides of this equation, and we see that v is equal to the square root of AC r. Now, we want this to be the case where the acceleration that we feel is the same as the acceleration of gravity on Earth. So this becomes, AC now becomes g times r. And we know that g is equal to 9.81 meters per second squared. And here I'm not caring about the negative sign on g because remember, so since we don't know the direction of AC from this formula, since the velocity is always changing, well, then this is really the magnitude of the velocity. So we don't care about the direction. So I'm just going to replace g with 9.81 meters per second and r with the radius, which is 200 meters, which was given by the problem. So we have 9.81 meters per second squared times 200 meters. All of those under the square root. So now I can get my calculator and I can input this value. So we're going to have the square root of 9.81 times 200 all under the radical sign. And to a decimal value, that gets me a velocity of 44.29 meters per second. We've got a meters times a meter, so this is meters squared over seconds squared. So when you take the square root of meters squared over seconds squared, you just get meters per second, and that's good. That's what we want for a velocity. So that tells us that the velocity needs to be 44.29 meters per second for this given cylinder of 200 meters. So that 200 meters affects the velocity. It affects the acceleration that you would feel. If you had a different radius here, you would have a different value for v and a different value for a sub c. So that's pretty cool. If you have this value v, then you're going to feel the same acceleration. If you're standing inside this cylinder and you're flying through space, you would feel like you're on Earth. You would feel the exact same acceleration. You couldn't distinguish between, if you were in like a closed room with no windows, you would not be able to determine whether or not you were on Earth or if you were flying in space, because you would be feeling the same gravity. And to give a real-world example of something like this actually happening on Earth, there are amusement park rides called rotors. And they're not very common anymore. There was some safety issues with them, some accidents. But basically what would happen is you would walk into this cylinder, and the cylinder would begin to rotate. It eventually sped up fast enough where there was so much centripetal acceleration on the people inside the ride, feeling themselves pressed against this wall, that you could actually lower the floor and you would stay stuck to the wall. So the ride would be oriented in this way, if this is the ground, and it would spin and it would go around and around and it would spin very fast, and eventually you could drop the floor and you would stay stuck to the sides. This is someone inside the cylinder. You would stay stuck to the walls of the cylinder. So it's pretty cool. So that's one example of uniform circular motion. We're going to be working more examples so we can become familiar and comfortable with the concepts.